and welcome to another episode or webinar of Teaching Grade 12 Mathematics. Today we're joined by Leigh. Hello, Leigh.
Hi, nice to be back.
Good to have you back. And of course we have Dylan behind the buttons, making the magic.
Hello.
Yes, and Leigh, did you notice my shirt?
I did. I love it.
It's a triangle, for those of you who can't see, in honor of our topic for today.
Very appropriate.
Yes, and what is our topic for today?
Euclidean geometry for grade 12.
Whew.
Yes,
you know, I've been nervous about this all week because Euclidean geometry was not something I really enjoyed in high school, and it's not something I ever taught either.
Now, that I can understand. I know when I was at high school, it wasn't my favorite thing. I could do it, but it was never easy. And only when I taught it, I got to really love it. And now it's one of my favorite topics.
Well, then I'm very glad we have you here. Maybe you can make me feel more at peace about it. Leigh, why don't you tell us a little bit about yourself?
Yes, I am in a position in which they give the title Master Teacher of Mathematics. Ridiculous title, but basically what it comes down to is I'm responsible for the development and the vision of mathematics in our 10 schools in our group.
Okay.
So, yeah, it keeps me out of
So
mischief.
are you in the classroom?
I do guest appearances. I miss not being in there more, and I'm trying to arrange for next year to actually have a class and share it with somebody. Because,
Okay.
working between the schools, it's hard to have one school with one class. So I'll go and do section teaching in certain schools.
So you support teachers who
Yes.
are teaching mathematics?
Yeah, and if they find there's a section like this one that's we're going to discuss today that they'd like me to do guest appearances and show them how I would teach it, I'll go in and do it. Or otherwise I'll sit with them, plan and prepare, and we'll go and let them do it, and we'll talk about it afterwards. So,
It's actually very useful to have someone like you
I
to
actually
bounce
think
ideas off. And
it's fabulous. I would have loved to have been in that position when I was teaching, to have somebody to just share with and that sort of thing.
yes,
So yes, I think it's it's a nice thing to do. It's
yes.
fun.
Okay, and remember you can join the conversation by either logging into Twitter and using the hashtag MEMaths, or going onto the Facebook page, which is the Digital Classroom South African Facebook page, and then making comments on the post that you'll find on the page over there. And we've got something new and exciting. If you are communicating with us and talking to us, and you could possibly win 55 Rand Vodacom airtime.
Always a good thing.
Oh, save money everywhere and win money elsewhere. Also, watch out for the secret code that will appear somewhere on the screen at some point during the show. But we've talked enough about that. Let's talk about the interesting stuff, which is not quite Euclidean geometry yet, but the book I've been reading recently, which is Teach Like a Champion. And if Dylan can bring up the slide for us.
Okay.
The next slide for us. There it is, Teach Like a Champion. I'm going to read it first, and then I'm going to tell you why it irritated me. This is Technique 11. Okay, maybe I should start by saying some of the other techniques haven't irritated me at all.
In fact, most of them have not, from what I've worked out.
Yes.
Yeah.
But this one did. The heading was rather, it sounds nice, draw a map, and then it says the classroom setup should suit the objectives of the lesson. I made it sound a lot nicer than the way it was phrased in the book. Basically, in the book, they're saying that the default position for your classroom should be rows, and there should be very little distractions on the wall until you actually need an object in the class to demonstrate something. Then you put that and only that up on the wall. So basically, you have a classroom which encourages conformity.
Pretty clinical.
Yes, and I know this does work for some people, and I'm not saying that it's the wrong thing at all, but what I'm saying is that it rubs me up the wrong way because I am not that way. With my kind of teaching technique, I prefer to have them bouncing ideas off each other as well as having my input. So for me, setting up groups or having them clustered, maybe not in groups, makes me feel more at peace.
Well, certainly with the topic we're dealing with, it does help to have them talking to each other.
You think so?
Definitely.
Because
It takes away that feeling of I'm on my own, no one's out here to catch me as I fall. And, it just makes them feel a little bit more secure.
yes, if there's one place I've had maths anxiety, it would be this section. So, yes, I would think so. And it does make sense that the classroom setup should suit the objectives of the lesson. For instance, if you're doing a test or an assessment and that you need to take in the marks, then separating them.
Then the default one is a good one.
Yes.
Yeah, but otherwise.
Yeah.
Look, it could help a little bit towards discipline. That might be the reason why it was suggested. And also, I suppose, by taking away the atmosphere of the classroom, you could also focus them a bit more, but I think you lose a lot in the richness of what you do in teaching.
It plays into that whole teacher-centered approach of teaching, and it does work. I'm not saying it doesn't work. There are situations where teacher-centered teaching is good. My personal, and that's why I say it irritates me, is not teacher-centered at all. It's bouncing ideas.
Yeah.
Yes.
I understand that. I can relate to that very distinctly.
Okay. If you do have any comments on that, if you think I'm a complete idiot and everyone should be sitting in rows, make some comments on the Twitter stream or on the Facebook.
I think with the sizes of our classrooms nowadays too,
Yes.
to have your children sitting in rows is about an impossibility. Your classrooms are built for, say, 30 children, and you might have 50 in there now. So to put them in rows is also just not feasible.
But groups actually take up more space.
Not really. It depends how you organise them. I can agree with you if you're sort of positioning them all so they can watch the board. Yes. Then it could take up more space.
Good
But
point.
if you're putting them in groups and the ideas they are going to teach themselves or learner-centred learning, then it doesn't matter how you do it, and it could be quite economical putting them in groups.
Yeah. Well, you could definitely have two people sharing a desk.
Definitely. Two together is great. Even pairs. Sometimes pairs are better than groups because you get more participation.
Yes.
Whereas in a group, if it's too big, you might have one or two people parking off and not really getting involved.
Oh, you always will. They're teenagers, aren't they?
Oh, they are.
Yes. Okay, now let's go and look at what the CAPS document says about
Definitely.
Euclidean geometry. And the next slide tells us we have, 2 slides on, unfortunately.
Okay.
There we go, the CAPS document, and it's got 2 points basically. It says revise earlier work, and then it also says prove accepting results established in earlier grades, blah, blah, blah. I'm skipping ahead to that bottom sentence,
The serious one.
which worries me, and it says allocated 2 weeks of teaching time, but marks are 1/3 of the second paper. So the second paper is worth 150 marks.
50 marks is sitting in geometry. 50 to 53, actually.
It's a sixth.
I know, it's very scary.
And only 2 weeks.
In 2 weeks?
Mm.
Something's gone wrong here.
Well, you see what it is too, is they're also taking into account the grade 11 geometry.
Wow.
But even there, it's not an excessive amount of time. I might be wrong, but I think it's as much as 3 weeks. So even 5 weeks worth of work for 1/6 of your mark is very scary. And I think that is what teachers are going to be so careful with, because it's so easy to think to yourself, well, it's only 2 weeks of work, we'll whip through this and we'll be on our way. But when you look at the amount of marks it's going to count, for me, it's disproportionate for how much time you get.
And I know in the CAPS document, it doesn't actually have that sentence at the bottom of that section.
No,
You've got to
it's-
go to the front to find
hiding.
that out.
It's in that little front section where they give you like a scheme of work and they
Yes.
say how many weeks, and then in the very front where they give you mark allocation, and that's where that little time thing is, the 53 marks.
Yes.
And it's a very scary thought. I've tried to raise that with lots of our heads of department to be aware of that, because you can so easily fall into a trap here.
Oh, very definitely. I think especially because grade 10 focuses on all that basic stuff, like parallel lines and proving that they're, I don't know.
The grade 10 is all that midpoint theorem, your quad theorems, your that sort of stuff. It's not enthusiastic kind of geometry, but very important stuff. And it almost, in fact, I think you could use less time in grade 10 and borrow that time for the top end, but it doesn't work like that because you're sitting in 11 and 12,
Well,
having
that's
not
my
taught them in
thought.
10.
Yes, because it's 3 weeks in grade 10 that you spend on going over the basics.
And they've already dealt with the properties of a quad and things like that, and they're not going to ever really use those theorems as proofs later on. It's a pity, really, but I suppose there might have been a reason behind it, which we
Don't they
know.
add to what we need, or aren't they building blocks?
Yes, there are building blocks, but I think for when you think you've got 2 weeks in matric with effectively three theorems, although the one is an offshoot of the other, it's still quite hectic. You're basically dealing with each theorem in 1 week.
Yes.
So 1 week on your proportion and then 1 week on your similarity with your Pythagoras. And it's the most beautiful application of similarity when you see the proof of Pythagoras. It's like awesome to see that, because they've never really see a proper proof of Pythagoras till they're in matric. And so it's a pity to rush it through. I would be happy if it was 2.5, 3 weeks in your grade 12 years.
Yes.
That would be more realistic for me. I think you're going to have to push the packet a bit to get through.
And it would be 2.5, 3 weeks to teach the content that's within the CAPS document for grade 12.
Correct.
And an extra week maybe to revise what's in grade 11.
Well, that's what I'm going to suggest that the teachers do, is that they try to build that revision in wherever there's a possibility. I know in the CAPS they always leave like a week at the end of thing, but quite honestly I think it's going to be run-on time because there's not copious amounts of time for any section. But I would suggest that they try and build that revision in somewhere along the way in worksheets and stuff like that, or maybe even have a revision class after school and say, right, we can revise your thing, but of course then you don't get everybody coming and you really need everybody there.
Yes.
That is the problem.
But maybe the ones who aren't coming wouldn't have got it anyway. Sure.
Well,
Helen, that's naughty.
I don't know if I believe that you can't get it. I believe you can to a great extent. I don't believe you can always solve everything, but there are techniques in geometry that make it very doable to an extent if you use them, which we'll talk about a little later on. But yes, I suppose it's true those children who wouldn't come would probably be your children that don't like mathematics very much and aren't going to achieve generally in it because they don't like it more than any other reason. But maybe you can also borrow from some other sections where you have more time. So, okay, let me zip a lesson or two from this because I can manage to teach that. I know patterning and your arithmetic sequences and series.
Unfortunately, those sections they're gone. We're just left with this and statistics and probability.
Yeah, look, you do have those two things still in your matric here, and you can go and learn a little bit of time there, I think. You probably could manage, because, you do arithmetic sequences from grade 8 onwards, just not formally.
Yes.
So you could certainly borrow some time there, maybe. And I could have to think about other sections you could borrow time from.
So that's a good plan for the future matrics. But
correct.
For these
this
matrics,
one, you are in the situation.
If you haven't
already
done revision already, then
you could be under a bit of pressure because you're now starting your third term with basically your geometry in it. So you need
I wonder if
ready.
it would be advisable to do not homework classes, but just added extra. Do this, I'll help you if you have problems.
Yes, I think it's a good idea. I don't think you have to do everything, but certainly you could give them, to revise the theorems, perhaps like a hint sheet or something, and say, okay, these are things, write down what you remember about your theorems, something like that, just to help them to get that grounding in place.
And of course, if you would like them to revise on their own, they can always go and look at the mindset resources.
Oh, thank heavens for that. That would be good.
Yes, and that they can do on their own if they have access to...
Yeah, they've got access to the technology. There are ways. Those mindset things are great.
Yes.
So they can go and get them and go through them. A lot of the times they reteach a whole section in one of those slots. I know I used to do them, so... Yeah, I know, you'll take a section of grade 11 geometry and you'll teach it from start to finish.
Yes.
So, yeah.
I know as a teacher, when I was starting out, I used to watch the videos to brush up on my content knowledge before I taught it. They saved me many times.
Yes, I'm sure.
Shall we move on to the 5-point teaching strategy?
Yes, definitely.
Okay, and that is the first point says make sure the necessary basics are in place so they do not hinder the learning.
Correct, and that's what I was meaning when I was talking about you must make sure they've got to know their Euclidean geometry from the first little fact that the angles around a point add up to 360 degrees. So some of that stuff, we take it for granted they know it, but probably the teacher skimmed through it previously and they don't remember it. So that is something they really need to go back.
I think, who doesn't know that angles around a point equal 360?
You'll be amazed. You'll be amazed at how quickly children forget things like that. I almost would spend, if I had time, I would take a lesson and literally sit and go through them and say, right, first theorem you learned was angles around a point. That equals 360. Here's the proper reason we use for it. All right, next thing we learned, the angles in a straight line add up to 180 degrees. Here's the proper reason for it. And I just let them develop almost like a cheat sheet of all the theorems they should know from previous years.
Ideally, they should have been developing this cheat sheet from grade 10.
Another way of doing it is to sort of do it for them and say, here's a cheat sheet of it. Anything that you don't remember, we need to recap.
Yes.
That
But
might
that's
save
really a
time.
last resort, isn't it? Because if they haven't written it themselves,
They won't remember it.
it's, yeah.
Yeah, so I think the ideal, and that's what I always used to do when I taught the geometry, I'd always develop it for them in a lesson. I'd take a 40-minute lesson, sit down and just go through the whole lot, every theorem they know, show them little funny ways to remember them. You know, like I'm sure you've all heard of the windsurfer theorem. That's the children's way of remembering tan chord theorem. You've got to imagine that the tangent is a little thing you're standing on, and the little triangle in the circle is actually the wind, the thing that's catching the wind, the sail.
Okay.
You're holding onto it, and that angle is equal to the angle coming off where you're holding onto. They've got little gimmicks that they remember these things, or the bow tie where you remember that the angles tended from a chord are equal.
Yes.
So those kind of
Vaguely
gimmicks,
ringing
yeah,
bells.
to help them remember them.
Yeah.
Yeah, and of course I'm a great believer, as you'll hear just now, on visually learning your theorems rather than verbally learning them.
Yeah. Your second point says, explain the theorem in a visual and numeric fashion.
Yeah. You know, I'm a believer that if you start by saying, right, here's your theorem, let us teach this theorem. Before you get the first 5 minutes of your lesson done, you've lost half your class, because it's hectic, rigorous geometry that they're going to find hard to engage with. And then they think that because they don't understand the theorem, they won't be able to do the problems. And so I almost ignore the proof of the theorem, and I show it to them in picture form rather than in word form.
Okay.
I'll say the words, but I won't write them down.
Now, we've just been talking about bow ties and about windsurfers. So you're not talking about bow ties and windsurfers here. You're talking about the actual diagrams.
Yeah, the ones that I can show you perhaps on the screen here.
Absolutely.
If I'm going to teach in this one, I'm going to say, okay, if I've got a triangle, what this theorem says to me, and I draw a line anywhere, ooh, lovely, and that line is parallel to that line, then this theorem tells me that this length over this length equals this length over this length. And what I would do is I'd say to them, draw any triangle you want. Put your line anywhere you want to put it. Measure. What do you notice? If I take A and I divide by B, stick it in your calculator, tell me what you get. C and divide by D, what do I get? And I show them that, yes, look, it won't be exactly because they've measured and there's an error, but pretty much that's equal to that there. So I'll show them that, and then I'll say, okay, now we know that no matter where we put it, we will get the same fact. And this helps them to start thinking. So that's what I mean by visually showing them.
Okay.
Rather than giving them words. Because if you say the line drawn parallel to the third side of a triangle divides the sides proportionally, I can tell you right now, those children are no longer with you. They are
I must
out of
admit,
there.
I'm not with you. When that language starts flying around, I don't understand what's going on.
Yeah, and that's why I think avoid that initially. Show them something practical like that. And then you can even take it a step further. You can say, okay, if this measures 14 and this measures 7 and this measures 10, what would this length be?
Okay.
So get them to think about it. Well, if the ratio has to be the same, 14 over 7 must equal 10 over what? Well, 14 over 7 gives me 2. So the only way for that to happen is for this to have been a 5. So they're starting to get the concept of the ratio happening incidentally. And well, that's what I would encourage them to do.
Yes.
Anyhow.
And of
I
course,
can see you
if
a bit
they're struggling with fractions.
Yeah, that's also a bit of fun and games, of course. That is the problem.
Yes.
But then also you get a chance to revise it in that concept.
Mm.
But if they see it like this and then you give them some numerical problems like this, it just makes it accessible to them. They think, okay, this is not so bad.
Yes.
And then when you start throwing in and then you make it a little bit worse, so you say, okay, fine, instead of using this, let's say this is 10, this is 5, and this is x plus 1, and this is, I don't know, let's give it a value. Let's say 3. What is x? So you make it a little bit more abstract. They've still got to realize that 10 over 5 is the ratio 2 to 1.
Yes.
Which, of course, is an interesting fact. And this ratio to ratio, that means that this must be 6. And we would solve that equation.
Yes.
So that sort of introduces a bit of abstraction, and then you could get even further along by introducing another x variable over here. And then they'd have to work out an equation involving x and numbers. So it's a slow move from the concrete to the abstract. And again, it comes down to we always learn better concretely than any other way.
So you wouldn't throw this at them in their first question, even though they have the skills?
Yeah, no, I would probably start by just drawing the picture, showing them with visually how it works, and then I would give them some like these with just numbers. I certainly wouldn't hit them with that.
Okay.
So I would give them different values for this. The same drawing, I could stick whatever I like there, 21 and 7, and then they would have to realize the ratio is 3 to 1. But they wouldn't even have to even consciously do that, because they'll just say, okay, well, I times by 3 to get that. So if this one is 15, what do I have to times by 3 to get this? It must be 5. So you're starting to build that concept of ratio indirectly, without even mentioning that that's 1 to 3.
But shouldn't they be guided through that step by step? Why are you leaving them to multiply it out?
Well, I don't think there's anything wrong with it, because if you like saying to them, I know that this over this gives me the same answer as that over that, they are forming that concept without even writing it down. So yes, by the time they get to write it down, so now let's say that's what we're looking for, let's call it X. Now they'll be easy. They'll say, well, I know that 21 over 7 must equal 15 over X.
So you're giving them this problem, but not telling them to
Correct.
write it down. You're just telling them to tell you what that value
What they would be.
is.
So
over there.
incidentally, they're doing it.
Okay.
And then I formalize it with the equation.
Okay.
So now they can see, okay, well, this will cancel down to 3 is to 1. Now I can start talking about the ratio 1 is to 3. It's also a great opportunity to stress to them that if I give them, and I was going to mention this later, but I'm going to mention it now, if I give them something like that, that does not mean that AB is 2 units long. Well, it is 2 units long, but let's say it's not 2 centimeters long and CD is 1 centimeter long, because maybe that's 20 to 10 or 200 to 100 or any ratio of things there. So that's a hard concept for a child to grasp.
Yes.
They should have done it in grade 9, but it's not something that we perhaps make specific enough in grade 9.
Yes. I think, yes. Then we're going into another set of issues about
Yes.
grade 9 teaching and things like that.
Yeah.
Okay. Your next point says work numerically with the theorem, and I think
So
that's what you're
I'm
talking
meaning
about over
yes.
here.
Yes, that's right. So that is what I'm doing. I'm sorry, I'm sort of like jumping the gun a little bit, but yes, that is my third point, that you need to work with it numerically like this to get the feel of it. And even when you get to similarity, you do the same thing. You say to them, okay, fine, yeah, we got a triangle. Yeah, we got a triangle. We know this angle equals this angle, that angle equals that angle, and this angle equals this angle. This is 10, this is 12, and I don't think it matters what I call this. Let's make it not maybe 6, make it a little bit easier. And this length is 6, so what would these be?
You know, in my head, all I've done is, well, if that's 6, that must be 12, and that must be 10. And then... yes.
Then we have a technical hitch.
Yes.
What I would do is I'd stress to them that the angles are important. So this is the side opposite the dot angle. So opposite the dot angle is 6, so those are the sides that relate to each other. Opposite the cross angle is the 6. Okay, so now what did I do with this one? Well, opposite the dot was 12 and opposite the dot was 6. I halved it.
Yes.
So this must be 3.
Yes.
And
that must be 5. Yes.
But maybe to avoid that, which you've just done, is if we'd played it safe and gone for a 4, and then if that is a 6
I think
or
that's
something.
a good thing. But I think what it does show is that if you think you've got this as a teacher, and then you put it up on the board and you quickly solve it with your first thought, and
You
of
could
course
be
your
in
first
trouble.
thought is not good because you haven't prepared it.
Oh, yeah,
Preparation.
that is my favorite thing. If you don't prepare every single question you're going to do. In geometry, I was fortunate enough to be in a position where I did a lot of group teaching, and I used to let them bring any question they wanted to me. And that was very good for the adrenaline, because you wouldn't know whether you were going to get something you could do or not. But it was also quite a good thing, because I think children must also see that we as adults need to stop and think. Sometimes it's not just instantly, here's an answer. We had to stop and think how we're going to handle it. And that's when I get to mention about techniques. So if they gave me something I had no clue, I'd revert back to my methods, if you like to call them that, which we will mention a little later on.
Yes, Dylan.
Can I ask a quick question, Leigh? Your suggestion here of working with problems numerically, does that tie into kind of the old tested idea of, because geometry is quite an abstract concept, trying to make it as concrete as possible to begin with and get people swimming with the fairy wings on before they're thrown into the deep end?
Fairy wings are very important.
Right.
Because it goes back to the Singaporeans who are so fabulous at mathematics. One of the things they always say, concept before procedure. So if you're getting the concept right and using numerical examples, then the procedural side is not hard. So if you make sure that they can do it numerically, then when you abstract it, you can always revert back. You can say to them, right, this is abstracted now, but remember how we did it with numbers. Well, we're not going to do anything different.
Okay.
And it just gives them something to anchor onto. I'm a great believer in that.
Okay. I'm trying to think which section it was, but I think we had a guest here once who said so with this particular section they must do routine, and eventually they'll get the concept.
Look, I suppose that's true. Routine would be considered numerical examples. So yes, that is, if you think of it like that, yes, then the routine would be what you need to do. But I also think, there's another thing the Singaporeans are big into, and that is that they say it's no good practicing something till you have the concept, because all you do is practice incorrectly the concept and you formalize it.
Now that's profound. You need to write that down somewhere so I can put it somewhere.
Sure.
No good practicing something
till the concept is formed.
Okay.
So when they teach, they will spend a lot of time getting the children to investigate. And one of the things I've noticed about watching them teach, they very seldom say you're wrong or you're right. They don't use those words.
Okay.
And so the reasoning, when I asked the guy, I said, why don't you ever say you're wrong or right? He said, because they may be not wrong, they're seeing it a different way. And so you need to get them to unpack what they're seeing and change to what they should be seeing.
Okay, I'm sure you're seeing crazy eyes coming back from me because I'm thinking that it's maths. You are either wrong or you are right, and you can shelter their feelings. But
yeah, no, it's not even sheltering their feelings. It's just understanding why they are seeing that problem. You see, remember, Singapore is very much word-based problems.
Okay.
They do a lot of geometry. In fact, they do geometry in grade 6 level equivalent to our grade 9s and 10s.
Okay.
So they don't spare them. Believe me, they do very complicated geometry. And there, of course, you can't really have a problem saying, well, there's a problem, but not a word problem. But certainly you've got to understand why that child or that group of children are not making sense of what you're saying. Are you phrasing it incorrectly? Ask them back. So what are you understanding by this question?
Okay.
Let them express what they're understanding. And often in that, you clear up misconceptions.
Or maybe they're not expressing themselves
Correct.
with the right terminology.
And often if you say, now, who got that answer? And they look around the class and they see that they not many people have got that answer.
Yes.
Then they question their understanding of what was said or done. And that's much more powerful than you telling them what is wrong or right.
Yes.
Because then they change their understanding and move on. So it's very interesting.
And it's a choice then. It's not
Correct.
enforced.
And if it's not enforced, I mean, I don't know if you ever watch Caesar Milan with his dogs. He always talks about when you put a dog in a car, you let the dog actually step in. You don't lift it in.
Yes.
So it's their choice to go into the vehicle rather than to be traumatized and put in it. Same sort of thing. Don't traumatize the child.
Okay.
Let them move to it naturally.
We are getting slightly off
Sorry.
topic.
We've gone to lots of things.
Yes, so let's go back to the 5-point teaching strategy, which the next point says, move towards abstract problems.
Right.
What is the difference between the problem you showed us just now with the fractions versus an abstract problem?
Yeah, abstract problems would probably involve, they would give you a kind of drawing. It would still have the parallel side. You would still have this kind of stuff in here. C, D, E, whatever. But they would ask you to prove that AC over AB equals AD over AE. So they've taken the numbers out.
Okay.
So now it becomes very abstract. They were doing it just now with numbers, but now there are no numbers there.
Okay.
So now they've got to make sense of what that means. And that's where I'm a great believer in colors. So I encourage the children, I usually say to them, go home, and if you've got a younger brother and sister, raid their pencil pot or their crayon pot and bring them in and highlight. Because if you highlight the sides, it becomes easy to see what's going on. So if you look at it like that, there's your AC to AB. Now, if that theorem is true and we know something about fractions, then we know that this must be true too.
Okay.
So that's what I mean by abstraction. So where they've seen it with numbers, so say you had a 4 and a 2 here and a 8 and a 4 there. Now they can see, well, 8 and 4 makes 12, and 8 over 12 is certainly equal to 4 over 6.
Okay.
But now I've taken the numbers away. So if they've encountered it with the numbers, it's not such a big shift for them.
So it's basically abstract problems are doing the same problem, but without any
numbers.
Variables or numbers.
Sometimes they'll throw a number in, like they'll do something like this. They'll say they'll cross multiply it or something, and they'll have a twice whatever in it, just to throw them. But it's not really a number. It's just double whatever the length is, rather than anything else. So yeah, that's the kind of thing I'm meaning by abstraction. Of course, similarity lends itself to it much more, and we're going to look at a similarity problem just now, and I'm going to talk about some methods and techniques, and I'll mention the abstraction again at that stage.
Okay. The last point says, now prove the theorem with rigor. Now, when I think of rigor, I think of 18th century movies. What do you mean?
Rigor mortis? No.
No, I'm just thinking earnest.
What I mean by rigor is where you actually take that first theorem we did,
yes.
I mentioned earlier, where we now say, right, this is A, B, C, D, E, and what we have to do, we know those are parallel. We're required to prove that AD over DB equals AE over EC. So now you have to know. So this would be
the formal
proof.
Then this, then
Correct.
This, therefore this.
Yes. Now, children hate learning off by heart. It's a dying art. So what I try to do is to teach them a technique rather than step 1, do this, step 2, do that. I say to them, okay, how are we going to do this? Well, all we need to remember is we are going to use areas of triangles to prove this question.
Okay.
And we're going to remember what our construction is. And our construction is we join up these guys.
Okay, so the rigor is proving
Rigor is the
theorems.
actual proof, and it's what the part that the children hate.
Okay.
With a vengeance.
I have an embarrassing question to ask you.
I'm sure it's not.
I don't know what a geometric rider is.
Yeah, rider is well, I can say old-fashioned, but it was the word we used to use when I went to school, which was many, many moons ago. And it basically is a problem.
Okay.
And we used to have funny little things. We used to go QED at the end of the question, which meant it was proved, and those kind of rigor things. So you will come across it. But basically, a rider is a problem. So it's something that we've given them to prove or solve or do, and we call it a rider.
It's just a question we would give.
Correct.
And the rigor is then proving a specific theorem.
And using the proper notation. You see, I just did an informal thing where I showed them a few examples. Perhaps we can use I can never say that word.
GeoGebra.
That thing.
Yes.
Or Geometer Sketchpad, and show them like many examples of numerical things that work, and say to them, all right, well, this is what the theorem's saying, but we're going to prove it later. And I think proving it later takes the sting off the tail, because by the time they get to prove it, they've used it, they're comfortable with it, and it's not that stressful for them.
Okay.
For me, that's important.
Yes, Dylan.
That's really interesting. I was always taught, and I taught geometry by you first prove the thing.
That's how we were taught.
And then you use it. But you've turned that completely on its head. So by the time learners come to proving it, it's like an old familiar friend, something that they're very, very comfortable with working.
They're much less likely to opt out. In fact, most teachers that I speak with regularly have just changed to this. Because I know when I was at school, as you said, Dylan, that was how you were taught. You were taught the theorem, the rigorous proof, and then you were allowed to use it. But by the time you got there, you were already zoned out, because they had used all this funny language and scared the living daylights out of you.
Oh, yes. I remember I'd worked out that I could still pass maths if I left out all the geometry and got 100% for algebra.
I think you were not alone, I hate to say. You had lots of company. In fact, it's quite not a joke really, but it's something that markers always say, we'll mark the geometry in matric final. Because it's the one that doesn't get done, and you'll see some of the things that I raised just now, basically it gets left to last.
I'm sure it does.
And often it's not the hard marks.
This conversation leads nicely into your 3 pressure points, because they all talk to this mindset, don't they?
Yeah, so let's look at those because that is exactly it.
And your 3 pressure points say that the first one is you can either do geometry or you cannot. Now, are you saying that that's the truth of it?
I do not believe that at all. I really think that with effort and with proper exposure and perhaps a little bit of gentle coaxing, most children can access a certain level of geometry. Whether they can prove these hideous riders from hell, that's another story.
Okay.
But then you're not looking at everybody being able to do that very hard rider. 50 marks, you're talking either 5 questions or maybe 4 questions with some theory.
Okay.
And of the 4 questions, they're not going to all be hideous questions. They're going to be some accessible to all. And so I don't believe you can say that you can either do it or not, because that's not true. I know when I was at school like you, perhaps geometry was not my favorite thing. I used to do it, but it was never my favorite. And I used to always look for problems in it. I thought it has to be difficult, and I'd go looking for difficult. In the meantime, often it was not difficult, and I'd make a big mountain out of a molehill. And so, I think that's one of the problems that comes up. So I don't believe that you can't do it. I believe that there are some people that will never be able to prove the hardest rider in the whole wide world on their paper under
just
exam
like
conditions.
There's some people who would struggle with the hardest algebraic.
Correct. It's
whatever.
not going to, the section does nothing. And often an examiner will set the geometry saying this is easy marks. So, the 4 levels, they would say this is knowledge. They always think that proving a theorem is knowledge. And if you analyze the paper, the theorem proof is the worst done question on the paper.
Yes.
Because they're trying to remember off by heart. And all the examiner does is change the letters.
Yes.
So where they've learned A, B, C, and D, E, F, they've now changed it to S, T, V, and
they've flipped it upside down.
And they've turned the drawing around a bit, and that's a big problem then, because they're actually incapable of doing it. And one of the things I always tell my pupils when I first start teaching Euclidean geometry with them, I say to them, as I said, think in picture form. Don't think in words. And I say, for example, when you were a little tot and you were walking around and your mum said to you, over there's a chair, and you looked at the kitchen chair. A little bit later, she told you the one in the lounge is a chair, and it looked totally different to the one in the kitchen. Then she walked into a shopping centre and she showed you a bar stool and said, that's a chair. And they didn't look at all alike, but somehow the concept of chairness came through to you. And you knew what its function was and how it worked. Even if it didn't look exactly the same, it was a chair. Same with geometry.
Okay.
So if they spin the drawing around, they make it look a little bit different, so what? If you look hard enough, you can see it. Another thing I tell them, and this is also not very good thing, so you might shoot me for telling them this, when people forge signatures, they forge them upside down.
Yeah.
Now, the reason they do that is the other side of your brain starts working and sees more detail. So turn your picture around.
Okay.
Turn it on its head, turn it on its side, do whatever you have to do, just so that you can see more detail. So there's absolutely, I'm glad you know that, Dylan, so I'm not the only reprobate here. It's good. You obviously tried to forge your mother's signature a few times too.
Very successfully.
Me too.
Were you ever caught?
I was.
Absolutely not.
I was. Never again.
Yeah, I didn't know about that turning upside down at that stage, but now I do. So, that's why it's important to change the perspective of the thing you're looking at. Because if you walk into a room and you look in a room, you see certain things, but if you stand on the other side of the room, you'll see something completely different.
Yes.
Same principle.
Okay.
So don't be shy to do that. That's all good technique.
And I was listening to a talk show recently where they were talking about the hidden curriculum and the hidden messages that come across. And I think I could have, if I had taught this without having the conversation I've had now with you, where I'm feeling more at peace, I could have very possibly stood up there and taught with a lot of fear.
And of course, let me tell you, that comes straight through to the children.
Yes.
They know. They know you are afraid. And I think that's what happens to a lot of our primary school teachers who didn't like maths at school and now have to teach it. And they go in and they're scared of it. And because they're scared of it, it comes through to the children. And then the children become scared of it.
And then we have the problem with fractions.
Oh, yes. They do not go away. They stay put.
Yes. Your next pressure point says there are no techniques you can teach your pupils to make the section more accessible.
That is so not true.
So
There
it's a
are
lie.
It's a complete lie.
Myth busted.
Myth busted completely. There are definitely techniques you can teach your children. Ways of looking at the drawing, for example, using your colours. I'll show you
turning
some
it
just
upside
now,
down.
turning it upside down. All those things help them to see a new way of doing it. And I'm going to show you some. When I was at school, which, as I say, was a long time ago, we used to do mathematics and a separate subject, arithmetic.
Yes.
I don't think anyone else in this room has been around as long as me, so you won't know about it. But this arithmetic was basically millions of fractions. So you were a fraction expert.
Fantastic. I like it
It
already.
was actually very good. It
Yes.
was actually excellent. I think you had like 2 lessons a week, so it was nothing major, but you got a separate mark for it. And believe me, you'd learn because it was marks on your report. And then one of the things they taught you is logic. Now, logic is a big factor in our geometry, and you're going to see when we get to the problems, I'm going to mention that again. So there are many ways you can think it. And little things that the symbols and stuff in geometry tell you that help you to prove a problem will also come up just now, which means there are certainly techniques we can teach our children.
Okay, good. And the last one says geometry should be left to last as it is time consuming. Well, hasn't the CAPS curriculum done that for us?
Basically, it has. It is time consuming, and giving it 2 weeks is not an indication of the time consumingness of it. But what they do is, the children are scared of it because they think they won't get very far. One of the best things that happened to me in my teaching career, there was an examiner in place, I can't even remember where I was teaching at that stage, who said, if the children waffle in a question, they're not marking it. So unless the question is going somewhere, they're going to stop marking it. And I thought, because before I used to say to the children, just write down everything you can see. Because at least somewhere there'll be some marks. But then I realized he's not going to let us get away with that anymore, and best I'll teach them something else. And that's where I'm going to show you some of those techniques I showed them.
Okay.
But even if they couldn't prove the rider, they could certainly get 2 marks out of 4
Yes.
for just doing this little trick I was showing them.
And once again, a rider is a problem.
Sorry, I keep using the word
No,
rider.
I'm
It's
just
from
making sure
my
I'm
old
understanding.
school teaching.
As long as I'm on the same page as you.
You are.
Yes. Okay. So we have looked at the CAPS document. We have looked at the 5-point teaching strategy and the 3 pressure points. Now we're going to look at something called tips and tricks. And we're at 3:45.
So I better talk fast.
Well, not so much fast, but maybe highlight the things
What's very
because I would
important.
like to go through
I'm
that
always
diagram.
thinking if we should go straight to the diagram, because in actual fact these points and tips will come out as part of the drawing.
And I can put it
And
in the
that's- I
blog.
think
So
it's a
read
good
the
idea,
blog.
yeah.
It will be available on digitalclassroom.co.za/webinars.
Yeah,
Did you
that's
see?
great.
Said it without taking a
In
breath.
ease.
Yes. So
I think
watch
let's
the
move
blog and I'll
on
put
in
all of
rather-
those.
yeah.
Let's take a look at this diagram. Not this diagram.
One
Sorry.
more?
Next slide. Next slide.
Sorry,
slide,
we
next
jumped
Yes,
through
we're
the slides here.
Jumping that one.
Yes, there you go.
Okay. Now, we had a conversation before this.
Yes, we
And
did.
you said this kind of diagram could actually even appear in a grade 9 exam.
Correct. You can use the same diagram in so many different contexts. If you did it in grade 9, this particular drawing, you could fill in some angles, maybe make that top one a right angle, and ask them to find X and Y and Z and P and Q. Obviously, you won't use the tangent because they won't know what a tangent is. You could maybe use the triangle there. And so grade 9, yes, you could certainly use even grade 8. When you go to grade 11, you could use your circle theorems, which are
Okay.
quite considerable.
Yes.
And you will see them coming out there. And then, of course, where I was going to use it, which is in your matric work.
Yes.
So it doesn't matter what level you're on, you can actually use that same drawing in so many contexts. And as I said to you earlier, in actual fact, if you start looking through past paper booklets, you'll be amazed how many times you will see that drawing. If
It's
you
a
go
good
and look
drawing.
back, it's got lots of richness in it. You can
Yes.
use it in all sorts of options. But if you go and look back on past papers, you will see that drawing in a form, maybe with one line different or something like that. But basically that frame used in many ways. So if you do enough past papers, and this is now after you've got the concept, of course,
Yes.
so the practice is good, you can then really like say, okay, that's the same sort of drawing I've seen before. I know the techniques I need to use on this drawing. So that's one way of the practice being useful and helpful.
Okay. Now, at the top it says, give them a blank drawing and encourage them to spot as many theorems as possible.
So a nice portfolio piece would be to give them a few drawings like this.
Yes.
And say, okay, this exercise is about you looking at this picture and seeing your theorems. So this will encourage the visual recognizing of the actual theorems. So if we look at the first one after this, Dylan, the next slide, you'll see I've highlighted in red a theorem. And of course, if they know their theorems, that's your tan chord theorem. There's your little windsurfer idea that I was telling you about. You can imagine the little man standing there. And what I would do is I'd say to them in the thing, so, okay, a question could have been, and I would let them put labels on it. If I say put that label on the tangent as A, I could say A1 equals C1.
Okay.
Or something like that. Or I could have made those lines equal and said, right, prove it, and then I had to use isosceles and that. So there's lots of things you could do with that drawing to find that. So a good exercise would be to say, recognize the theorems, and then think of 2 or 3 questions you could use with that particular theorem.
That's quite a higher order skill.
Very much a higher order skill.
So you would do that kind of exercise towards the end of the 2 weeks of teaching this?
Yeah, I would actually use it almost as a start.
Oh, really?
In terms of revision, because if they're doing this now,
that makes sense.
They would be revising their circle geometry indirectly. And now if we look at the next one, I think I've highlighted a cyclic quad, if I remember rightly.
Yes, in green.
Yeah, so you can see there's the cyclic quad. So now what theorems are to do with cyclic quads? Or maybe we can prove the exterior angle equal to the interior opposite and use it in some kind of problem. So you can think about ways to use that. To actually make the questions would be a higher order. Perhaps I'd leave that to the end. But to identify the theorems within the picture, I would do early.
It's almost like the old word search activities that they used to do.
Mm.
And spot the cyclic quad, or a where's Wally activity.
I've got a Wally shirt. I should have worn it today. Yeah, so that's one of the things. And then I think I've even got one where I've highlighted the parallel lines, I think.
And that would be the grade 9.
Yeah, and even the grade 11s and 12s, because they forget that those theorems come with them.
Yes.
That they're not a little island where those don't count. So what will happen is they'll get stuck. Dylan's taught geometry, so he knows what I mean. They will get stuck trying to use their circle geometry and other geometries, but not think about the most obvious one, which is their parallel line.
Or the
which
tools
will help
lying
them
at
out.
the bottom of the toolbox.
Yes, dig them out.
Yeah.
And so, yes, so that's 3 things that I could see, and you could think of some options you could ask on that quite easily too. So, perhaps the first level of this would be to let them identify, and then the second level say, okay, what questions could we ask?
Okay.
So that would give you the sort of easy level versus the more high level thinking of designing questions.
Now, that kind of activity, would that qualify as an investigation type
Yes.
activity?
Yes, definitely. I'm the portfolio moderator for the IB, and I would be delighted if I saw something like that come up in a portfolio.
Hint, hint, nudge, nudge.
This is my last year, guys. Work quickly.
Okay. Well, I know that you've set 2 questions for us to go
Yes, I'd
through
like to just
using this.
mention those, because
Yes.
that helps us with the rigor. I think
The
it's
rigor is the proof.
The techniques that I would use.
The techniques.
From the rigor of the mathematics. So I'll
Okay,
explain
I've
it
just
here.
remembered a question that I really, really wanted to ask.
Sure.
And it's something that's always bothered me.
Want to be?
The reasons that you have to write down. Is there a set list anywhere?
There is a set list.
Okay.
They used to exist in the textbooks.
Yes.
But there's a nice maths website that runs. It's called Maths FET website.
Dylan's going to look.
Yeah,
Google
if
quickly.
you go on that, and you've got to belong to it. So I don't know if you'll pick it up there. So what you have to do is you would have to send an email to Stephen Sproul, and he would put you on the site. And the moment you're on it, we share that kind of thing. So someone will say, do you have a list of reasons? And out will pop this little list of reasons.
I don't know how I don't know of this site.
It's a very useful site. It was actually started in the private schools, but it's not only private schools on it, it's anybody, really.
Oh, good.
So, it was started initially by them when they brought in curriculum 2005. Did it not
Okay.
come up? Okay, the best
But
is
you
I
will
will
send
give
through
you
the details
I
and
will
I'll
give
put
you
them
the
on the
email
blog.
address to contact. And then
Okay.
you go on and you'd ask to join the site. The reason he did that is because he didn't want outside people from the country joining. So he didn't want Americans and that sort of stuff, because
Yeah,
then it would,
they
it
mustn't
would
come with their
change-
radians and
yeah, it would
yes.
change the nature of this. This is a South African site for South African teachers within the South African curriculum. And you'll get nice things like questions that come up. Look at this question. What do you think of it? How would you do it? And the discussion that goes on is really very nice. So I will send that across to you so you
Thank
can
you.
get them to email him and just ask to join the site.
Once again, check the blog post. I'll post all of this
Yeah.
information.
And as I say, he just didn't want other countries, because then it changes the nature. He wants this for South Africans. So
Okay.
that's why it is closed as such. You have to be invited to it.
Yeah.
It's easy enough though. Great.
Okay,
So
I
let's look at
interrupted
this
you. You were
question.
talking about rigor and something backup knowledge.
Yeah, so I think perhaps if we go to slide
The numbers have
the
changed
numbers have
since
changed, so
then.
it's not going to help. I think it's that one where they ask you to prove the triangle's similar. Now, if you've taught your children that sign, that similarity sign that you see there, as soon as that's there is a convention, and that is that whatever's over here, it means that this must equal that, this must equal that, and this one must equal this. Otherwise, we do not use that sign.
Okay, this is the
I did
similarity.
not know that.
No, Dylan.
I did
I
not
don't
know
Even
that.
I knew
I
that.
think lots of people don't know that, Dylan. I don't think you're alone at that at all. So if they've asked you to prove that, you're halfway there, because in actual fact, you know that A must equal D.
Yes.
You know that B must equal E, and you know that C must equal F. And all you've got to do is look at that drawing and figure out which one will work. Now, if you look at that, you can see that A will obviously equal A because it's shared between the two triangles, the red and the blue.
Now, why must we write it down then? If it's obvious, why?
Well, it's like when you go to court. It might be obvious you didn't do it, but they're going to insist on some kind of proof. I always relate to geometry as a kind of court case. You can't just say, I didn't do it, Your Honour, and finish going kaput, although some people do try that. It doesn't work. So you have to say, I didn't do it because on such and such a day, at such and such a time, I was here. Give a reason.
Okay.
So the rigor of geometry is just that. You have to make your statement and substantiate it with something that has been proved or established. So it's just like a court case. So in this case, I would make sure that when I taught this, I would write my triangles. So I'd say in triangle, and I'd write the red triangle on the left, and I'd write the blue triangle on the right, and I'd make sure that as I proved it, I showed them equal in that order. So obviously I can see that A will work with A.
Yes.
And it's easy to see why. It's because it's shared or common. But now if I look at this one here, the B equals
Dylan,
the
can
D.
we put it up on screen, please?
Oh, sorry.
Sorry,
Thank you.
Dylan, I
Thank
went
you.
off that. Yeah, sorry, I didn't realize. Yeah, if you look at the B equals the D, that's
Yes.
also easy because you can recognize the picture of tan cord.
Okay.
So those two are things. So say, for example, they had unpacked this as a different order.
Okay.
And the one that's not easy to prove, which is that third one, was first. So then that's fine. All you do is in pencil, you write the three things down. You see which ones you can spot the quickest, because you only need to find two of them. Because if two angles of one triangle are equal to two angles of another triangle,
Then the third
because of
one's
this
automatic.
angle, some of the angles in a triangle being 180, they're automatically equal. So we only ever have to prove two.
Okay.
Now, some teachers don't write the third one down, but I think that's a mistake too, because that third one there is useful for them when they write up their similarity.
Okay.
So they might change their order to what was asked, but as long as their order is consistent, so in other words, the first thing they mention is equal to the first thing they mention on the other side,
Yes.
that's fine. And it also helps them to draw up their ratios.
okay.
So that's an important thing. So say, for example, I had proved, sorry, Dylan, I'm now going back to the screen. I'm jumping around here. This story over here. And I write down triangle ABC, similar to triangle DEF. Of course, I've got to give the reason, which is equiangular triangles, or you can use angle, it's up to you. Once they're there, I know that this angle equals this one equals that one, and that equals that, even if they had given it to me in another way. So when I come to draw up my ratios, I don't have to go back to the drawing. I can almost cheat. And this is something that most teachers get right very quickly because it makes life so easy for you. You'll take the first two over the first two. The last two over the last two, and the first and last over the first and last. Then, whatever they've asked you to prove with, say, something squared or something, you could tick off which ones you need, cross out the fraction you don't need, and it's as easy as anything. So those are all techniques that are good. Now, one thing that children don't realize is when there are 4 parts of a question, so say the first one asked you to prove that similarity. The second one asks you to prove that AB times EF equals BC times DE. They can't prove the first part, that's fine. They just say, assuming A true. And they use what they were trying to prove at the top to carry on the question. So then they carry on with B. But they've said it's true. They've assumed that they've lost those marks. But they can carry on and get the marks for the next bit. That's why I say it's not true that you can either do it or not. Because if you've got that fact that those are similar, you all know how to draw up those ratios really easily.
Yes.
So you can, even if you just do that part, even if it's 2 marks out of a 6-mark question, it's 2 marks you wouldn't have had if you left it out. So I'm a great believer in that style of teaching.
Okay, we have
run out of
2
time.
minutes
Oh,
left.
2 minutes, okay.
And I would like to show the GeoGebra links.
Yes, that's great. Can I just mention one thing here before we do that? If we got this question and we asked to prove this, a very good skill for them to learn.
And there's a time sign over there.
It's a time sign, over there. If you look at it, is how do you select the triangle? So what I suggest they do is they take color and they highlight AE.
Yes.
Now, AE is twice, so I know it must be in 2 different triangles, so I'm going to highlight it like that. And then I want AD. AD is this long one. So that already tells me it's that big triangle for one of them.
Okay.
See how easy it makes it for them to choose what to use. And then the AC is this one, and so I can use that smaller triangle there.
Okay.
So that helps them to identify
so
which 2 triangles.
Because that is coloured in red and this one over blue, in blue, we can see that this triangle will be used.
That's right.
Then because this is dashed, the CA is dashed and EA is dashed, we know we're going to use this triangle over here. What about all these other bits and pieces?
Well, they might help you prove something, and they probably do, because if you're going to have to try and prove this, you're going to have to use a technique or 2. But it helps you. So when you name it now, you can say in triangle AEC and triangle DEA. Notice the order doesn't matter there.
Yes.
Because I'm not really worried about that sign yet. Once that sign comes in, I've got to worry about it. Then I can see, right, this is a shared angle. Now I've got to find one more fact, but it's not going to be so easy. And they haven't given me the order, so I can't cheat like I showed you just now. So what I've got to do now is I've got to think, okay, well, let's start with this angle. I know it must equal this one, because that's the exterior angle of a cyclic quad.
Oh, my word. Yes, it is.
But because those are parallel, that is equal to.
Dylan's laughing at me.
Don't worry, I understand, Dylan. It's not fun, this. So what I'm doing here is I'm showing you another technique that we're not going to get time to look at.
I see the F. Yes.
We want to prove C equal to E. So literally what I've done is I've separated them like this, and I've said, well, C is equal to G, exterior angle of a cyclic quad. And E is equal to G. Because they're both equal to G, C equals E. And that's from the arithmetic syllabus we did in grade 8.
Yes.
So that's a technique that's very useful when you have to prove 2 things equal. Sorry, now we can go to GeoGebra. I had to show this because I think it's a very important skill.
I think it is important. Yeah, I'm feeling a lot more at peace about this section.
It's a lovely section. It's really enjoyable.
I just wanted to show these 2 links because I like them.
They're fabulous,
they're
actually.
To the proportionality theorem as well as the midpoint theorem. And Dylan, can you click and drag some points? Basically, they're demonstrating the ratios, that they remain constant. And you can compare different... Oh, I didn't even click on those.
That can actually give you the theorem coming out there beautifully.
What a great teaching tool.
Actually, that's really nice.
Well, the link will also be on the blog once again. Another reason to come visit us.
Best part, it's free, this link. So
Yes.
it's really worth getting to know it.
And then the other one, which is useful for grade 11 Euclidean geometry as well, is the midpoint. And there you can drag around the points of the triangle in all sorts of directions. And you'll see that...
And what's nice there is you're seeing that the length of those two parallel sides are in the ratio 2:1.
Yes.
And of course that reinforces that theorem, because the ratio would have been 1:1 on the sides. So the small side against the big side would be 1:2.
Okay,
And
it
that's
took me
why
a
it
while
works.
to click what you were saying. It's the
Sorry.
the midpoint. No, I'm just slow. It's the line across the midpoint of the triangle is half the length of...
Of the bottom one.
Yes.
And of course, that's an important thing for them to know too, because if you start working with those parallel sides, you can't use proportion theorem. You have to use similarity,
Okay.
unless it's midpoint, in which case you're
I feel
fine.
like we're opening up a whole nother conversation,
Keep
which
quiet.
is interesting, but I need to stop it because we're now over time. And Dylan, have we had any interesting posts? Okay. Well, if you saw the secret code and you want to share some good teaching resources with us from this section, you can stand to win a tablet or a phone.
Or a phone, yeah.
Yeah.
That's
And it's a
fabulous.
tablet or a phone that I would like.
Yep, it's a Galaxy
Yes.
Tab,
Oh,
7
nice.
inch.
7-inch, and a Sony Xperia L.
Yes. Also very nice looking.
I
I
love
looked at the
that.
pictures. They're fantastic. So find the secret code, go back and rewatch the webinar, then submit your entry with your resource to competitions@digitalclassroom.co.za, and we'll be posting them up on the Digital Classroom
You might
website.
see me submitting my one.
Make sure you read the terms and conditions.
You are ineligible.
Unfortunately,
How unfortunate.
and we'll see you again next week when we talk about grade 10 finance and growth. Leigh, we won't be seeing you next week, but
No.
it's always wonderful having you.
Well, I've enjoyed it again, once again. You got me on a topic. The assessment I loved, and this one I love. These are my passions.
I'm very glad to have you for it. And thank you, Dylan, for all of your
Thanks, Dylan.
magic. Join us again next week. Bye.